So, quick recap. Now, all of you, I'm sure, coming to a venue like this for an event like this don't need to be told what a container is. So first of all, let's start with what's a container. All right. Containers are lightweight. They're hermetically sealed, isolated, easily deployable, introspectable, and runnable Linux processors. They're really nothing more than that. So like starting an app on your phone versus booting your phone up, that's the difference between a container and a VM. So we're all aware of that in the context of system administration. Throughout the day, some of the other speakers will talk more about how they're using this technology in different areas. Why we like them? Well, they improve the overall developer experience in a number of ways, foster code and component reuse, and simplify operations for what we call cloud-native applications. There are a number of popular container runtimes: LXC, RKT, following the TLA theme, obviously, the Dockers. A quick recap now on Kubernetes. You're going to need to laugh harder than that, or else by the time I get to the one joke in the presentation, you're going to be very disappointed. So, what exactly is Kubernetes anyway? We take an ocean of containers, we schedule them dynamically onto nodes. Handle lifecycle and health, scaling, naming and discovery, finding where these things live, load balancing across these containers, providing data via storage volumes, logging and monitoring, debugging and introspection, and then identity and authorization. So once you have these processes, the tools for managing VMs, the tools for managing physical infrastructure no longer apply. We need a new set of tools. Influenced by the 15 years of experience that Google have in this space, we've released Kubernetes to the public, pattern compatible with what we do internally, but not repeating all the same mistakes. So I mentioned cloud native. We think Kubernetes is one of the 3 legs of cloud native. The other 2, of course, container packaged. We don't need to go into that. And using microservices architectures. So using Docker and Kubernetes together is a fantastic way to build yourself a scalable microservices architecture. We announced Kubernetes June 2014. It's now been GA for over 1 year. We are, of course, 1 week away from the release of 1.4. So beta dropped yesterday. If you want to try that out, we'd very much love to see people try it. We've got some swag coming for the people who do. This is a graph here from the OpenStack folks who look at such things, and it's not correct because there's a lot of people who they don't quite know where they fit. But overall, what I want to point out here is that it's now less than half of the contributions to Kubernetes have come from Google. Obviously, it's something we worked on internally, seeded to the community, has now been picked up by a number of great partners, vendors, community members, hopefully a lot of you in the audience today. And because this is something we very much want to share with the entire industry, we set up a foundation for it. So under the Linux Foundation, we set up the Cloud Native Compute Foundation to spread these ideas and to work with products that make sense together. And we're seeing there's 2 projects now on the CNCF, and there are a few more underway. I want to point out that Kubernetes is very, very stable, and this isn't just in a case of rock solid and operating environment. Built, as I say, on top of our ideas and production containers over 10 years now, and a lot of the mistakes that we've made. We have a consistent API. We don't make breaking changes to it. So we've gone 1.0, and what that means is that API is now solid. We're building alpha features and beta features on top of this, but until we think they're ready, and that's we as in the community, not we as in Google, we are holding them until the next version of the API. But most of the new work that's needed is not in the API. In large part, we think that that's complete. There are plugins for things like volumes and networks, so extensibility. People can write custom controllers. There's a lot of great work going on in watching these resources and saying, all right, what do I need to do in my cluster in response to that? And then if your resource doesn't exist inside, what you can do is create a third-party resource and then add that to the API. We do thorough end-to-end testing with every release on more and more providers and platforms. It's built on top of a very solid core. So the core primitives haven't changed a huge amount. We have pods and services and volumes and labels. Again, I'm assuming most of you are familiar with this. If you want to ask any questions, please come up to me at the end. And we're iterating on top of those basic building blocks. So for example, Ingress was introduced about 1.1. It's a way of connecting a load balancer to a service. A ReplicaSet is a a set of fungible replicas. So we have things where it doesn't really matter, there shouldn't have any difference between them, but we want a certain number, and that'll come in important soon. Daemon sets, jobs, obviously, and scheduled jobs are being released in 1.4. We have a fantastic ecosystem. So a bunch of cloud providers there. Again, I don't think I can read them on this tiny little screen, so please excuse me. But a number of fantastic partners building things in open source, a lot of people taking Kubernetes, letting you run it behind the firewall, building connections to their storage and networking things, building monitoring. Prometheus is the other project that's in the CNCF at the moment. But a very, very healthy ecosystem. Some great momentum. So just that number's now from a couple of days ago. We've just gone over 35,000 commits by 880 people. And a number of great companies have gone Kubernetes in production, and call out to Pearson based in London. I don't think any of the other customers there are London customers, but all around the world. So a few quotes from, you can probably guess where they're from. This one I like, it says, "This is the best infrastructure I've ever used in 20 years of doing ops and leading ops teams." This one says, "We reduced our bill to 30% of our original price." And then there's that one. So I just want to quickly see, is Ilya in the audience from Weaveworks? No? Or he's being very quiet if so. So one of the things that's being worked on, again, primarily in London at the moment, is a tool called kubeadm, which is a tool for bootstrapping a Kubernetes cluster. In the past, we've built GKE, which is our hosted version, and obviously Google say this is a great way to get started, but then there's kind of a ball of shell scripts and things to get running on other providers. So we're making this a lot easier. Basically, 2 commands. You run one command on the machine you want to become the master, and then you get given an auth token, and you share that out to other machines. Eventually, there'll be a gossip protocol to make that a lot easier, and that'll be the way that you bootstrap a node. So I want to point out that this is available. There's some great videos from the special interest group doing cluster lifecycle. Ilya and Luke from Weaveworks published one just a couple of days ago where they show this off. So anyone who's interested, it'll be available in alpha in 1.4. I would very much like to get people playing with it. So of the 2 topics I wanted to address today, the first one is moving beyond stateless workloads. So what problems are we trying to solve? It's obviously very simple to run stateless workloads where we just throw however many replicas we want at the problem. But for a lot of cases, think things that need storage, think databases. First of all, we need to preserve the individual identities for these fungible entities. They are not now just things given a code name randomly every time. We want some kind of ordering. We want a predictable ordering, and we want control of that order so that when we want to scale more, we add them to the end, and when we want to maybe scale down, we take them off the end. So we always have 0 to whatever the maximum number is. We want the other entities to be able to identify each other if we have a system that needs some kind of quorum, or if we want to something where it needs to communicate with the other peers in the cluster. And those nodes will need some kind of consistent storage, and that will need to hang around and stay with its node, because the identity corresponds to data in the cluster. Now, we have a little digression here. And I have to apologize in advance, because there's a very, very horrible metaphor that we use here. It's flawed in many ways. Unfortunately, it's kind of the best we've got. It encapsulates the idea. It's the best we've come up as an industry, deeply flawed, only really worth being written in Comic Sans. It's pets versus cattle. Now, aside from the fact it's offensive in a number of different religions, it's a flawed analogy for a number of reasons. First of all, sometimes pets are indistinguishable from cattle. Sometimes cattle are pets. Sometimes cattle are just plain adorable. Cattle are supposed to be fungible, but sometimes they come pre-numbered. And it's not just the pet part that people take offense to. All right, so obviously naming things is hard. Everyone's familiar with this. It's one of the 2 hard problems in computer science. In fairness, I could tell you the UDP joke, but I can't guarantee that you'll get it. So what exactly is a pet? So the object inside the pet set ensures that a specified number of these items, these pods, with unique identities are running at any given time. The identity of a pet needs three things. It needs a stable host name, so it can be found in DNS by outside tools and by other people in its own cluster. It needs an ordinal index, so it needs a number starting at 0, because we're all nerds. And it needs some sort of stable storage, which is linked to the ordinal and the host name. So we have a user here communicating with the Kubernetes API running on the master node. And they say, we want a replica set. This is the old way. This is for stateless services. And we'll say, I want 3, please. And we get 3. And what you'll notice is that in the case here, we're starting a web pod, and it just gets allocated a gibberish ID at the end so that there's no conflict between them. But there's no relationship between these things. They are fungible. They can come and go. We might want to introduce an autoscaler to this situation. So now we have a robot talk to our API, and it says, actually, I'd like 6, please. And so we scale up and we add a few more. What now if we say, OK, well, we want to scale down? So in this case, depending on scheduling policies, depending on how you set your cluster up, you might have any number of things happen, but there's no guarantee. So it might be that those are the 2 that you end up keeping. And you might decide that depending on full cache, you want to keep the oldest nodes, or you might decide based on, like, well, there's gremlins, I want to keep the youngest ones. But in this case, the idea is they're fungible, and the system will just do what it wants to do. Now we introduce the pet set. We say, we'll take 3, please, with some storage. You define a template that says, in the alpha case, we say basically how much you want dynamically provisioned. And we end up in this situation. So now we see we're actually asking for a database in this case. You'll end up with a persistent volume claim, which is Kubernetes' way of claiming storage from an environment, which is set up by an administrator. And that could be automatically provisioned on a cloud, or it could be something that the admins have said you have access to this. And then we have a volume which maps the claim to the pod. It's a one-to-one mapping. And only when that first one is set up completely do we get a second one. And so on, we now have our third. Let's say now that the human decides, again, well, these are things I care about as pets, so I'm going to scale down to 2. So what we're going to do is cancel the the highest numbered one, the lowest one on the slide. But because we assumed that there was some data in that, we might want that again. We might eventually want to scale back up and reattach that data. We might want to go through and look at it later. This is something we care about. It has important states, so we're going to keep that volume claim around. So what other problems do we have in this kind of environment? We have now an ability to say, I want a cluster of things that are aware of each other. So they need a way of finding each other. So we talk about peer finder, which we can either do at startup, or sidecars, which again is a way of attaching 2 containers together inside a pod. And then we also need a way of ordering operations. So when you start something that wants to elect a master, or you start something that wants to attach some data. So we've introduced InitContainers. Init. So in this case, we may say there are things I want to do before my main container starts, and my main container should only start when those things are finished. So we might want to mount some things, or attach that volume, copy some stuff off that to the root file system perhaps. Perhaps we want to say, well, I'm going to use the service to call out and find who my peers are and then feed that into the config file for my application who needs to know to be able to talk to them. So I might call out to DNS, write a config file, and then and only then when those things have succeeded, we do the thing we actually came to do, which in this case, again, is be a database. So PetSet is an alpha at the moment. It will remain an alpha in 1.4. The thing we're really blocked on at the moment is we want to see more people make more prototypes. We've seen some work on Cassandra. We have MySQL Galera. There are a few things in there. And you can click that link with your mind and check them out. But we really want to see a few more things there. And I want to call out to Jetstack, who, first of all, working on some ELK examples for this, contributing it back upstream, and also helped out by letting me steal some of their slides. So that's the storage and the stateful applications. Now we need to move beyond the cluster. First question, what's a cluster? We want to give you a feeling for how we operate things internally because we find that we don't want you to make the same mistakes. So a cluster is a bunch of machines on a high-speed network. That's our definition. What's high speed? Well, ultimately, it means in the same building. Most importantly, everything in a single cluster should have about the same latency to each other. If we take our pet example, if we need to do some replication between these things, if we say there's maybe 10 milliseconds between 0 and 1, and then like 150, 300 milliseconds between a third one because they're in different physical environments, then we don't know when we commit a transaction how long it will take to return. We don't have that consistency. So you should put those things, if they're geographically spread, into different clusters. How much is a bunch? Well, one of the things that you can do with containers is bin packing. And what you should do is size your cluster so that it's big enough that you get the advantages of bin packing. But it's not all your machines, because if you accidentally say, "Oh, take the cluster down," and you type the wrong thing, you don't want to kill everything. So what we will tend to do is within a building, we will have more than one cluster or more than one cell, which is the software we run on those clusters, so that we are safe in the case of accidental operator error. You may have seen these slides before. These are from the Borg paper that we published recently. But the point I want to make here is that the bigger the bin is, the better the packing you can get out of it. We found that if we took the machines in the cell that did the production work, which are the blue machines here, and then the machines that are doing batch work, so the things that are running in the empty space at low priority, the gray cells up the top. So we pretend that we've sized the cell so that it's only got the software running there. It doesn't have any overhead anymore. If we compact down and get rid of that, we're roughly at that blue line for a certain amount of work. And we ran a simulation, and we said that if we were only going to run the production work, then we'd save a little bit, but ultimately, the non-production work compacted gives you a 25% overhead. So another way of looking at that is by running batch and production workloads on the same clusters, in the same cells, on the same set of machines, we need 25% fewer machines to run the same amount of work. And these are advantages you can get by using a modern clustering system. So how do we separate our workloads? What do we want to do in the case of one or more clusters? First of all, if you're in the same cluster, just use namespaces. You can say, give this namespace to one group of people, give this to another group of people, and then you get the benefit of that packing densely all on the same machines. If you're running within the same region, perhaps in a cloud provider or something where you have some geographical spread, but it's very, very close, use node pools to create a regional cluster. So again, this is something you can do with a click on GKE, but you can also, with a command line or in other clouds, you can add nodes from zone A, basically tell it that you have multiple nodes, multiple zones, and it will spread your nodes as you deploy them throughout those zones. That way, again, if a single zone gets burninated, then you're fine. Within multiple regions is now what we want to look at. If we want to run places which are 150 or 300 milliseconds away from each other, this is where we introduce the concept of cluster federation, which was also once upon a time known as Kubernetes. So here's our single cluster case. We again have our humans and our machines talking to a master, running a bunch of different components. And then we have a bunch of different nodes which run things like the kubelet and the proxy and Docker or Rocket. It really boils down just to this. Users communicate with some kind of API, and then on the magic pool of machines, magic happens. Federation moves the layer of abstraction a little bit further up. And so now we have a control plane, which again looks kind of like an API. It actually speaks exactly the same API as Kubernetes, so you don't need to change anything. And then instead of having nodes on the right-hand side of this picture, you have clusters. Like the nodes in the previous picture, the nodes don't know anything about each other. They communicate their state back to the control plane. It makes scheduling decisions. The same is true in this case. These clusters don't necessarily have any kind of interconnect. They definitely don't need to know about each other, but they just report back to the federated control plane, and then you can make decisions. You can say, deploy this work and have it distributed globally based on whatever policies you want. So what does this look like? First of all, we create some clusters. In this example here, we use 4 cloud zones, and we like B for today, so we'll create them all in zone B in those 4 different regions. You can pick whichever method you want to deploy those. So now we'll deploy a federated control plane. It has a namespace, an API server, a controller manager, and a key value store. And if those things sound familiar, they are exactly the things that are deployed on a single clustered Kubernetes master. We're going to pick one cluster to run this on, so we'll just pick US Central 1 here. And now if we address kubectl with the federation cluster context, then we'll be able to address things to the federation rather than just to a single cluster. So we need, first of all, to add our clusters to this federation. So we have some YAML here, which gives you an idea of roughly what that looks like. Eagle eyes will see that this is super awesome, and I've gone as far as 257. So for each cluster, we run a command to add that to the federation. It's kind of like a Star Trek thing. New in 1.4, federated ReplicaSets. So we want to run a particular thing, and we want it to replicate. But again, we're worried that we might lose connectivity between these places, so we don't want to run just within a single cluster. We'll federate worldwide. So you say you want 4 replicas. By default, it will try and spread them out, but there are policies that let you say how you want to cluster them together. And ultimately, I say I want 4 Nginxs, and we get one deployed here in this example in each cluster. Now we need a federated service, which is a way for these things to be accessible to the outside world. So similarly, we say basically it's Nginx, we want to expose it on port 80. And what happens is a load balancer is created in each cluster. Each shard of the service, which we're now running globally across these 4 clusters, has a load balancer. Each service then gets a DNS entry. So what you see here is for our Nginx service, we have each cluster, so the US East, US Central, Asia East, Europe West, a load balancer gets that DNS entry. And then for the service as a whole that's federated across all 4 of those things, we get this endpoint, which will do round-robin DNS between the clusters that are running that particular work. In this example, it's all 4 of them. Let's say that we've packed them like this, and we have work running here in 2 clusters, 2 pods in each. So the user is going to look up where the service is running. So they'll make a call out to DNS. DNS will say it's running on clusters 3 and 4. The user says, thank you, that's great. And then their client application picks one of those values and connects to it. What happens in the case that one of these clusters is unavailable? Well, we'll turn that one off. The cluster will recognize and will spin back up to 4 replicas, which is what we asked for. So again, the desired state, the controllers will make that happen. And then the DNS response gives both of those clusters until it's had time to catch up, but then the client says, all right, that one's unreachable, and connects to the second one. So now we've moved on from operating within a single cluster space to global replication without any of the problems of lag, adding machines around the world. Something very, very cool which is coming out in 1.4, if you happen to be a cloud provider which runs a global load balancer, and there's only one that does at the moment as far as I understand, you can use the ingress to provide a single IP endpoint, which is available and handles that. So you're no longer doing DNS-based replication, and that can address all of your clusters. Cluster federation is in beta in Kubernetes at the moment. It came out in the last release. ReplicaSets and federated ingresses are new in 1.4, which is coming out again in a week. After that, we're going to add all the rest of the features that aren't currently replicated. Identity and access management, perhaps a hosted version of the control plane on GKE. This is our rough guess as to what we think the roadmap will be. But we expect, again, maybe a release in Q1, which 4.5 will be probably 1.6, that we'll call this generally available. But you can deploy this because this all doesn't change Kubernetes as a whole. It's just an application that sits on top and re-implements the API. You can deploy this today on any hosted Kubernetes cluster you want. A few more links that you can click with your mind, or when you get the slides afterwards. But we have some great blog posts. There's a walkthrough video from Kelsey and some instructions which will let you create what we created here on the slides. And I can't really pull that off, but anyway. 1.4 is coming soon. I encourage you, if you're interested in any of these great features, to come and have a chat with me or deploy the beta. It'll be out in a week's time. Whole bunch of things around Federation, whole bunch of new features which we are releasing in, again, whatever stage makes sense. A lot of things moving from alpha to beta. Alpha features can't be deployed on Container Engine, but we are going to have a way of creating clusters on Container Engine that run in alpha mode, so you're able to test some of these things very easily. A lot of the work I mentioned before about Easy Cluster Bootstrap, again, builds on top of that, so it doesn't require API changes. It'll be available for you to test, and I think that's actually around today. So, thank you very much. That's the end of my talk. I encourage you to tweet at me, tell me what you thought. Thank you very much.